Mathematical parallels, the equations describing the interior of a black hole, after crossing the event horizon, and an expanding universe, like our Friedmann-Lemaitre, Robertson-Walker metric, show striking similarities. In both, roles of space and time can exchange, and dynamics involve a trapped region, where all paths lead inward, for a black hole, or where expansion defines a cosmic horizon, for our universe. The horizon connection, both systems are defined by horizons that limit information and causal connection. A black hole event horizon hides the interior from an external observer. A cosmological horizon, like our observable universe's limit, hides regions of space that are receding faster than light can bridge. This structural similarity suggests our cosmic horizon could be the event horizon of a parent black hole. Solving the entropy puzzle, the early universe had inexplicably low entropy, high order. A black hole, however, has maximum entropy for its size, scaling with horizon area. If our Big Bang was the quantum gravitational bounce or transformation of a collapsing star in a parent universe, the low entropy beginning of our cosmos could be naturally generated from the high entropy state of that parent black hole. Singularity resolution, both the Big Bang and the center of a black hole are classically described as singularities, points where equations break down. Quantum gravity theories, like loop quantum cosmology, suggest these singularities are replaced by a bounce or smooth transition. Thus, a collapsing star in a parent universe could bounce into an expanding baby universe, our Big Bang. Holography and emergent spacetime, the fact that black hole entropy scales with area, not volume, hints that reality might be fundamentally described by information on a boundary, a concept called holography. If our universe is inside a black hole, all its 3D physics could be a holographic projection from data encoded on the 2D event horizon in the parent cosmos. This supports the idea that spacetime itself is emergent from more fundamental quantum degrees of freedom. Dark energy as a boundary effect, the mysterious dark energy driving cosmic acceleration could be an indirect signature of our embedded condition. Its value and behavior might not be due to a field within our universe, but a consequence of boundary conditions imposed by the geometry of the parent black hole and its external environment. Challenges and open questions. Testability, this is the greatest hurdle. By definition, we are trapped inside the horizon. Any signal from the parent universe cannot reach us. Evidence must be indirect, subtle imprints in cosmic microwave background patterns, the specific value of dark energy, or correlations in large-scale structure that seem unnatural for an isolated universe. Scale and dynamics, while the math allows it, making the detailed dynamics match our precise observations, inflation, nucleosynthesis, structure formation, requires fine-tuning the properties of a hypothetical parent black hole. Which black hole? If every black hole spawns a universe, we face an infinite regress. Is there a top-level, master, universe? This leads to ideas of a multiverse or cosmic natural selection, where universes that produce more black holes, that spawn more universes, become statistically dominant. Arrow of time, the hypothesis elegantly reframes the arrow of time. Our internal experience of entropy increase from a low entropy Big Bang is linked to the external view of a black hole forming, a higher entropy process, and then potentially evaporating. Biggest question to ask, as per the video prompt. If our universe lives inside a black hole, the biggest question might be: what happened in the parent universe to cause the formation of this specific black hole, and how do its properties, mass, spin, charge, parent physics, determine the fundamental constants, initial conditions, and ultimate fate of our cosmos? This question bridges the gap between the unseen exterior and our measurable reality. Its answer would tell us why our laws of physics are what they are, why the cosmological constant is so small, and whether our universe's fate, endless expansion, heat death, or a future crunch, is pre-written by its birth and collapse. Conclusion. The universe inside a black hole model is a profound, speculative synthesis that recontextualizes cosmology. It is not yet a testable theory, but a powerful conceptual framework that unifies the two most extreme predictions of general relativity, black holes and the Big Bang. Offers potential pathways to solve the entropy and singularity problems. Connects to cutting-edge ideas in quantum gravity like holography and emergent spacetime. It reminds us that our observable universe may not be self-contained. We may be living in a nested reality, where our entire cosmic history is but one chapter in a vastly larger, hidden gravitational epic. As research in quantum gravity and precision cosmology advances, we may find clues written in the heavens that point to this astonishing architectural layering of existence.